Good evening, everyone. Welcome.
Good evening.
Thank you very much for coming tonight. This is our opening tonight for our University of Richmond Museum's exhibition, Massive Rocks and Minerals, Selections from the Collection, which is on view beginning tonight and going through May 13th, actually, of next year. So we have it up for the entire school year at the Lora Gallery of Design from Nature. And immediately after tonight's talk, please join us for the reception with refreshments down at the Lora Gallery. And we'd love to have all of you come. So tonight, it's my pleasure. Excuse me, to introduce myself. For those who don't know me, my name is Matthew Howell. I'm the Curator of Museum Collections for the University of Richmond Museums. And tonight we are welcoming Dr. Robert Tracy, Professor of Geosciences and the Director of the Museum of Geosciences at Virginia Tech in Blacksburg. And the talk tonight is entitled Some Thoughts About Collecting Minerals and About Mineral Collections from Amateur to Professional. So join me please in welcoming Dr. Robert Tracy.
Thank you, Matthew. It's a great pleasure to be here, and it's an honor to be invited to kick off this exhibition. We were over earlier in the gallery, and I got a preview of some of the samples, and there are some really remarkable samples there. A very beautiful collection here, and I'm impressed. And a very nice and better space than we have in Blacksburg to display it. And please excuse me for taking my jacket off. It's came down out of the cold mountains down here to the coastal plain, and it's unusually warm here for those of us who come from the cold mountains. We also it was my first time visiting the University of Richmond, and I rarely make it to Richmond. We're sort of inculcated up in Blacksburg, all faculty at public universities west of the Blue Ridge, to avoid the place because typically nothing but bad comes from Richmond in our direction, at least in recent years. There was a time in the past when it wasn't that way, but it has been in recent years. So what I'm going to talk about is, I've never given a talk like this. I'm an academic and a scientist. I work on rocks and minerals in my academic research, and I have PhD students. So this is a kind of a departure for me, and we'll see how it works out. But what I wanted to talk about was a distinction. Matthew and I talked a little bit about how to theme the talk. About a distinction between collecting minerals and about mineral collections. Mineral collections having a sort of an implication in that term that it's an organized and professionally coordinated sort of thing. The American Museum of Natural History, the Smithsonian, the Los Angeles County Museum, big museums that have large staffs. Mineral collecting is something that almost anybody can do, and almost everybody has done. I'm always amazed when I go out into places where you can find rocks and minerals scattered around, particularly mineral collecting localities, and I'll show you in a while on a slide one of the more famous ones from New England, from New Hampshire. And I'm amazed at how avidly little boys in particular, and in recent time little girls as well, can't be kept from picking things up. And at the seashore they pick up shells, they pick up pebbles. They just are ready-made collectors. So I think many, if not most human beings are. What lies behind that psychologically, I can't say. I'm not a psychologist, but it's an interesting phenomenon. Let me tuck this out. So what about collecting? Collecting is, as I said, an interesting thing. A lot of people get sucked into it. Most people, and they'll collect virtually anything. I put some classic examples up here. Furniture. This is a Robert Goddard chest in the Metropolitan Museum in New York. Obviously, something that has very serious monetary value, if any of you know about furniture know. Antique tractors. I have a friend and colleague in Blacksburg in the forestry department who grew up as a farm boy in southern Indiana, and he loves tractors, and he collects them. Model trains or all sorts of other toys. I had Lionel trains when I was a kid. Some people collect campaign buttons. This is a brand new one. I just happened to hit upon it when I was Googling campaign buttons, and whether this has gets any traction, I'm not going to comment on, because this is not that kind of talk. Coins and stamps, dishes. People collect Fiesta ware from the 1930s. One of which, the famous radioactive red, has uranium in it and may in fact be dangerous, but people collect it anyway. So why do people collect? Well, there's just this desire to get things, but they also have in mind an aesthetic value. I don't see much, for me, aesthetic value in an old rusted out tractor, but I suspect my friend Jim Berger in Blacksburg really does see aesthetic value in that. And it's kind of nostalgia as well in cases like that. So aesthetic value, and this is certainly a major part, as we will see, about collecting minerals, is the aesthetic value, because they really are beautiful things. Some are not so beautiful, and a lot of the rocks I work on for research are just not ugly, but they have intellectual interest for me and my students, and scientific interest. And you learn a lot about the way the Earth works by learning how these rocks work. So aesthetic value first, then monetary value. Obviously, there's a wide range of monetary value. Something like this, I'm not an expert, but I would guess this is probably $500,000 worth of chest here in that Goddard chest, and some furniture is worth a tremendous amount. This we won't comment on again. But I'm amazed looking at Antiques Roadshow at how much value there is in old toys. Sometimes many thousands, even tens of thousands of dollars for old toys that are particularly with their original boxes. Collectors like that, and that's part of the collecting ethos. Intellectual value. People collect things because they are interesting for whatever reason. People have book collections where they just don't simply put the first edition, for example, but they don't just simply put them on their bookshelves. They actually read them and get something out of them. Historical value. There are lots of things that you can collect that have historical value. You could argue that in many cases minerals have historical value. Older furniture can have historic value. If you're into collecting Greek urns and ancient Grecian urns or statuary, Roman or Greek, there could be intellectual or historic value there. And scientific value, that's particularly a part of the picture with mineral collecting. People who collect minerals, in many cases, have an interest in putting them to use for scientific study, for determining chemistry, for determining crystallography, and things that teach you about the way the Earth works. And then the final, maybe overpowering reason is just because we can. And you should never, or I would never discount that. So many reasons for collecting. Let's see if I can read this. This is a really interesting thing. I got this off the web. It's kind of a definition of mineral collecting, since we're focusing on minerals here. Mineral collecting is the hobby of systematically collecting, identifying, and displaying mineral specimens. Mineral collecting can also be a part of the profession of mineralogy, which is what I practice in major part in my academic career, and allied geologic specialties. And there's one word in here that's particularly important, and that's systematically collecting. There are some mineral collectors, some actually semi-professional, if you want to think of it that way, mineral collectors, that may collect only one species of mineral. In fact, there's a rather well-known mineral collector and dealer in Northern Virginia, Victor Young, who collects essentially only calcite, calcium carbonate. And he has perhaps the best calcium carbonate mineral collection in the world. Amazing array of colors, different sizes, different crystal habits and shapes. And he is known to make those samples available to scientists who want to work on them. So there's a number of collections that have developed over time. The Geological Museum of London's been going for a long time, and if you go to London, you should go there, the Geological Museum and the Natural History Museum in London, and museums, I should say, as well, at Oxford and Cambridge, fairly famous museums, that started with a nucleus of minerals that somebody collected 300 or 400 years ago, and have been added to and supplemented over time. And that's the case with all of these. This is a very old one in Milan, the Museo Civico di Storia Naturale, the Natural History Museum in Milan, the Mineralogical Museum at the École Nationale Supérieure de Nîmes, the mining school in Paris, Philadelphia Academy of Natural Sciences, a very notable collection that very sadly, as is happening with a number of formerly professionally curated collections, is mostly been dispersed. In fact, the whole thing has been sold off to dealers. The Philadelphia Academy of Sciences lost interest in minerals probably 50 or more years ago, and they had this stuff there. We were given an opportunity, our museum was given an opportunity through the help of a very generous donor to obtain a substantial amount of that material. And unfortunately, we couldn't pull it off. But we knew that it was coming. Everybody in the community knew it was coming, that the Philadelphia collection would be broken up. There was a very famous collection at Penn State as well that recently was broken up into individual lots and sold off. And there's a terrific loss there, particularly if there's systematic sub-collections within the overall collection that they may never be seen again. When private collectors get these things, they may have them in locked rooms, and they put them in vaults and banks, for that matter, like people do with very valuable wines or fine art. And it's a great shame, because these are things that really should be shared with everybody. And that's part of the essence of collections, is that sharing them and sharing the pleasure of and the aesthetics of the material is a wonderful thing. The Smithsonian, of course, starting in the 1840s, in the United States, and then aggregating lots and lots of material since. The Smithsonian's one of the great collections of the world, of course. The American Museum of Natural History in New York, I ran out of space here, but the Los Angeles County Museum is a very major mineral museum. And then many, like the museum you have here, the museum we have in Blacksburg, small ones, university-related ones, and some that are not related to universities are wonderful resources for the community, just to go and enjoy minerals or to do a deal to get some samples for study. So here's some interesting minerals. This is uvarovite from Russia. It's a chromium garnet, beautiful. Doesn't show too well in this picture, but a beautiful green color from the chromium. The Star of Asia, Star Sapphire, one of the centerpieces of the Smithsonian collection, along with the Hope Diamond, which was in my title slide. And this is a kunzite crystal that is particularly aesthetically pleasing. There's something about really perfectly formed, what's called idiomorphic crystals, that have exactly the right crystal shape. This doesn't. It has crystal planes and then these terminations up above, but there's something really pretty. Even though it's not a perfect crystal, it has appeal, almost like a landscape. Now, a little sidebar on mineral names. Students are often asked me about this. What's up with mineral names? So you see this hodgepodge of names, and it's hard to kind of make sense of it. Is there any rule? Well, in an official way, the International Mineralogical Association has rules for what you have to do to get a new mineral characterized and named. But for minerals that have been around for a long time, the names have been around for a long time, the three primary things that have gone into naming are the places they come from, The people, either who discovered them or in many cases just people who someone wanted to honor with this name, and physical characteristics. So for example, aragonite, one of the varieties along with calcite of calcium carbonate, comes from Aragon in Spain. Andalusite, one of the 3 aluminum silicate minerals, all of which are in this slide, comes from Andalusia in Spain. That's the so-called type locality for it. Alleghanyite, which is a mineral I study, comes from Allegheny County, North Carolina, but there are significant occurrences in Virginia, in the Piedmont, on the east side of the Blue Ridge. For people, a very important one is silimonite, also Al2SiO5 with a different crystal structure from Andalusite, named for Benjamin Silliman. We'll see a bit more about him in a second. Lawsonite, named for Andrew Lawson, who was a longtime professor at Stanford back in the first part of the 20th century. An interesting one, armalcolite, an iron magnesium titanate, which is named for Neil Armstrong, Buzz Aldrin, and Michael Collins. Anybody remember who they were? This mineral happens to be found only, or until it was actually recently found on Earth, but until then it was assumed it was only in lunar rock. And so it was, when it was discovered and returned lunar samples, it was named after these guys. Uvarovite, which we saw before, chromium garnet, named for Count Sergei Uvarov, who was a very famous Russian diplomat of the late 19th century. Other characteristics, kyanite, the other of the 3 Al-silicate minerals, often in European languages spelled Cyanite, for cayenne, is named that because it's blue. It's not always blue, but almost always. Melanite, a variety of garnet, is black, and so the mela prefix refers to black. And rubellite, a very famous variety of tourmaline, dark pink tourmaline, which you'll see a picture of later, is from the Pala pegmatite in San Diego County, California, and is named for the pink color. So mineral collecting started a long time ago. One of the first really documented, and undoubtedly cavemen were, they're maybe picking up rocks more than minerals and using them to bash each other. but systematic mineral collecting with the notion of using these minerals to try to do something practical really is kind of traced back to Georgius Agricola, sometimes just called Agricola. His real name was Georg Bauer. Lived in the middle 16th century, and he's often referred to as the father of mineralogy. He was actually an early mining engineer and wrote much of De Re Metallica, his very famous treatise, is on mining practices of the 16th century. So you see here a kind of nice medieval view of, I guess it would be transitional into Renaissance view of people walking through the woods, picking stuff up, and you can see the miners at work, so the mining connection is there. A lot of mineral collecting actually started in the early days with miners and continues that way. Miners are a terrific source of really fine mineral specimens. And in fact, mining companies often, they want to share of it, of course, when a miner finds something really nice underground, and they try to police the miners so they don't carry the stuff away without recording it and paying a share of the ultimate price to the company. So switching from Germany, from 16th century Germany to America, one of the early pioneers of geology and mineralogy in the United States was Benjamin Silliman. He was from the class of 1796 at Yale. And was recruited by Ezra Stiles to go and be educated in chemistry and geology and mineralogy in Europe when he graduated, and then to come back and become a faculty member at Yale, which he did. And he was a professor for 52 years at Yale. He ultimately died in the middle 1860s. And he had a profound influence on the development of geology as a science. He lectured in both chemistry and mineralogy at Yale. And one of his things he's famous for is the Western Connecticut meteorite that was observed to fall in Western Connecticut in the Berkshires, Connecticut Berkshires in 1807. He went out, he actually found it and collected pieces of it, and they're still in the meteorite collection in the Yale Peabody Museum. He's one of the founders of the Sheffield Scientific School at Yale as well. And the collections that he established, including, this is not his specimen, but this is a specimen of sillimanite, the mineral that was an unusually gemmy one that was named after him. This collection formed an important basis of the Peabody Museum. Another early American that is of interest to me because I'm a graduate of Amherst College is Edward Hitchcock, who was a professor there of geology and natural history through much of the middle part of the 19th century. He actually saved the college from financial disaster in the early 1850s. And he built what was called a cabinet. The earlier slide about Silliman referred to the word cabinet as well. These were buildings that were designed, they didn't have quite the same meaning as what minerals are over in the Robbins Gallery, what they're housed in. This is a whole building that is designed to maybe have classrooms, but to house specimens and to house scientific activity. Because this Woods cabinet also had a telescope, an early telescope. In fact, it was here, and the roof opened up so you could see the sky. And of course, the Smithsonian Institution, a truly remarkable place. I suspect most of you have probably been there. If you haven't, you surely need to go. It was much inspiration to me as a young person. In fact, my father told me that I would want to go basically every week. I grew up in Alexandria, so about 4 miles as the crow flies from the Smithsonian, and I just could not be kept away from the place. And it wasn't just the minerals which interested me, but the stamps, the coins, the model railroads, and all the stuff at the Smithsonian, America's attic. But the minerals are a major part of it, and they are truly spectacular. And this is one example. This is all gold nuggets at the Smithsonian, a cabinet that has nothing but gold nuggets. This is all beryl crystals of one sort or another. Aquamarines, emeralds, pink beryls, just all beryl, nothing but beryl here. This, of course, everybody knows what this is, the famous Hope diamond. This is a beautiful sample. This is called the, lost it from my mind, but it's an aquamarine. It's been manipulated, it's been carved, but it's a Spanish specimen. Now, it's an interesting aspect of the Hope diamond that's shown here. The Smithsonian acquired it in 1958 from Harry Winston, the jeweler. It had, as most people know, a very checkered history and was supposed to be a very unlucky thing. This is how it arrived at the Smithsonian. Harry Winston just wrapped it up in tissue paper and put it in a box inside this envelope and sent it registered mail. Notice the address, Smithsonian Institution, Washington, D.C. You're not going to get away with that these days, I don't think. So this is how it arrived. But of course, the Smithsonian and most other museums have, especially ones that have a scientific mission as well as a display mission, have a back room. The back rooms of the Smithsonian are absolutely remarkable. The chief curator of minerals, Jeff Post, has taken me into the back room. There's probably 10, 20, maybe 100 times as much stuff in the back room as there is on display. And much of it is not quite as aesthetic as the stuff on display, but it's used for scientific purposes. And they request people send samples that have been published on to them for curation so that later researchers can get a hold of them. So a major aspect of mineral collections is the back room for scientific study. Now, mineral collecting can be done by amateurs, and this is the amateur aspect of it. This is a very important amateur mineral collector favorite. The Ruggles mine in Grafton, New Hampshire. It's a pegmatite, and unusually a rock of granite composition, but with crystals feet across, giant crystals. And there are beautiful things there. And I used to spend a lot of time there when I was in college. We would take little mini field trips up there and go camping and scrub through the mine and see if you could find something interesting. And there's a lot of good stuff there. And they advertise now. It's actually a tourist site. The Ruggles mine, the mine in the sky, because it's at the top of Isinglass Mountain in Grafton, New Hampshire. And these are all the minerals that occur there or have been found there. There's some really remarkable typos here. And here's the, your classic happy family at the Ruggles mine, spending a day collecting minerals. And it does happen. You go there and you see families, and you do that. You can do that as well down in western North Carolina, out by Asheville. There's pegmatites there. Spruce pine in particular has beautiful ones, and they've set up as a tourist enterprise. And you can collect some very good stuff there. So how does mineral collecting then, in the general sense, stack up in terms of motivations we talked about earlier for collecting? Well, it kind of checks the box on all of them. I didn't say it checked the box on this because you don't need to say that it checked the box on this one. So some defining terms, what's the difference between an amateur and a professional? Well, this is just off of Wikipedia pages. But generally an amateur is considered a person attached to a particular pursuit, study, or science in a non-professional or unpaid manner. Unpaid is one of the kind of key concepts here. And in fact, some of us who regard ourselves as professionals are not all that well paid for the mineral collection aspect of what we do. Amateurs often have little or no formal training in their pursuits, and many are autodidacts or self-taught in what they're involved in, what their interest is. But that sells them a bit short, because I know many mineral collectors that know more than most mineralogists about systematic mineralogy. So you have to be careful. You can't prejudge. Professionals are members of professions or people who earn their living from a specified activity, often referred to as their professional specialty. The term describes the standards of education and training that prepare members of the profession with skills necessary to perform the role. So where this enters into mineral collections is, and I regard amateurs as the folks who go out and go into abandoned mines like the Ruggles mine, tourist site mines, like the ones in western North Carolina, and for their own interest and gratification collect minerals. The professionals are the ones who actually have the often unenviable, as Matthew can tell you, task of managing a public mineral collection. And it can be a big headache, particularly the financial aspects of it. They're typically underfunded, and trying to get money to keep them going is not an easy thing. But that's fundamentally the distinction. Now, my own personal journey, if you want to view it this way, as the title suggested, from amateur to professional, started out, again, growing up in Northern Virginia with the Smithsonian literally around the corner. I was like a kid in a candy store. And I picked up an enthusiasm. I loved Jumbo the elephant in the lobby. P.T. Barnum's stuffed elephant that's there. And the dinosaurs and all the fossils, but I love the minerals as well. Then I went to college in New England, to Amherst College. I became a geology major, and I got to go to a lot of these really world-class collecting localities, some well-publicized, almost tourist-type places, and others not very well known, except in the geological community. And you camp out, you drink lots of beer, and you collect minerals, and you have a lot of fun. And that's part of your personal evolution. Then you go to grad school, and you become a mineralogist, petrologist, and you get hooked up to a major analytical instrument like an electron microprobe, various kinds of specialized highfalutin tools, and you learn to appreciate the intellectual and scientific value of those minerals that you used to collect, just for fun, because you could. And then I got after grad school, I got an academic job at Yale. I was there for 8 years. And I became curator of rocks and minerals in the Yale Peabody Museum, which is one of the great North American museums. It's most well known for the dinosaurs and for the famous Rudy Zallinger murals of dinosaurs in the wild in the Mesozoic. But it has a spectacular mineral collection as well, and I was in charge of that. And then when I moved to Virginia Tech about 30 years ago, I became, after I was there a while, I became director of the Museum of Geosciences. So that's a kind of a personal trajectory that's not an uncommon one for people that end up in the sorts of jobs that Matthew and I have. So I want to just very quickly go through a couple of more scientific things. One of the aspects of minerals that tends to attract people's attention is the apparent immutability. These are for the ages. They've been here forever. In fact, we now know that diamonds in the Earth, many of them actually have an interstellar history that goes back to the early days of the universe, to greater than 10 billion years of age. So these, there's a lot of recycling of minerals, they just hang around. Well, diamond might hang around longer than most because it's a pretty durable mineral. But there's some minerals that that aren't nearly as durable as we think. I'll show you a couple of examples, and they're important because they relate to preservation issues for mineral collections. And the first of them involves the mineral Proustite. I just love this quote, so I'll take the time to read it. It's from Wallace Terry, is a very famous mineral collector, and he has a mineral collecting blog, an outdoor blog. There are certain minerals that hypnotize the collector, some with their monetary value. This hits on the reasons or motivations for collecting. Some with their art aesthetics and others with their specimen fame and history. A few appeal to the most primal attraction, a fascination with rich and distinctive color. Perhaps no species in the mineral kingdom has a more unique and appealing hue and chroma than Proustite. Not named after Marcel, but named after a French mineral investigator from the 19th century. It's vermilion scarlet red, I'll show some pictures in a second, appearing to glow under moderately bright light, yet fleeting and fading with time. Mexico and Chile, miners use the phrase sangre de toro, the blood of the bull, when they encounter freshly broken rock that exposes Proustite or its relative pyrargyrite. These miners celebrated the rock bleeding with rich silver ore. It's a kind of poetic way of putting it, I think. And this is what they look like. This is Proustite, which is a silver arsenic sulfide. They're from a family of minerals called sulfosalts that typically involve a combination of metallic elements with both arsenic or antimony and sulfur. So its close relative, pyrargyrite, is silver antimony sulfide. And it's really, really beautiful red color. Some more examples. It's kind of, it's a red that you rarely will see in minerals. It's just, I've seen really good samples of it. But there's a problem with it. If you have, as Wallace Terry says in his blog, if you go out and buy a really beautiful specimen, you can't show it. You can't display it because it's very sensitive to light. Light destroys it. And the reason for that is because of the Proustite structure. This is the array of sulfur, arsenic, and silver atoms in it. And the way they're bound together, this is Einstein's harmonic model. They have probability ellipsoids of where the atoms actually are in the structure. So the yellows are sulfur atoms, this is an arsenic atom, and these are silver atoms. And this is a very loosely bound structure. The atoms can move around a lot. And if you look, there's a sort of a cage that holds the silver with sulfurs around it. And it's a loose enough cage that silver can migrate when energy enters the structure. And it's due to an effect called thermal vibrations, but it may have to do with heat, but it can simply be due to any energy, and light energy is as good as any entering the structure. So what happens is the silver actually leaves where it is in the crystal structure, thus wrecking the physical properties of the crystal, and you get something like this. So this is a Proustite crystal with tarnished silver blobs that have coalesced and migrated around within within the crystal, and you can see them scattered around on the surface. Obviously, this sample is scientifically really exciting, but aesthetically not nearly as exciting as the others. And ultimately, it can lead to this, which is threads of silver that have essentially been squeezed out of the structure as the mineral has been compressed in underground, but in a zone where it can be altered that way by light. And miners just love to pick up this stuff. And I find this one of the most beautiful things, mineral specimens I've seen in a while. And here you have what's left of the Proustite, which doesn't look anything like what it looked like before. A second example is pyrite. Pyrite, very common mineral, fool's gold. Pyrite, this is a great mineral for design in nature. It kind of looks like Frank Gehry could have designed this sample. A beautiful cubical form. It has various crystal forms. There's another really beautiful one. Interpenetrating twins of pyrite are particularly common. Spain has lots of really wonderful localities for pyrite. It has other crystal forms as well. But pyrite has a problem. And the problem is that, let me show a few more pictures. Pyrite also, iron disulfide, FeS2, chemically what it is, can actually replace fossil material. This is an example of an ammonite that's been essentially completely replaced, the outer shell and the septa, by pyrite. And you find many different types of fossils that are pyritized. And here's another good example of a trilobite that's been pyritized. But the problem is pyrite disease. Anything that consists of pyrite can get pyrite disease. And pyrite disease is basically a reaction of pyrite surfaces to humid air. It involves oxygen and water. And oxygen and water together reacting with pyrite creates sulfuric acid. And so sulfuric acid rapidly eats up the pyrite crystal, oxidizes it, and turns it into a mixture of hematite and sulfur. And so if a sample has pyrite disease, if you sniff a really good fresh pyrite, you won't smell anything. But a pyrite that has pyrite disease smells really nasty and sulfurous. And that's because of the free sulfur that's been released in the process. Whoops. The chemical reaction is shown here. And this is a reaction which happens very commonly at mine sites, both hard rock mines and coal mines, when there's sulfide present. And it leads to acid mine drainage, which is a terrific environmental problem. And this is what drains out of an awful lot of mines. It's not only nasty looking, but it's nasty because it typically has lots of heavy, often toxic heavy metals in it. This is incipient pyrite disease and outcrop. Notice the pyrite crystals are starting to get rusty, so they're indicating that this is happening. And this is when it's gone a lot farther. And notice something very, very interesting with this advanced pyrite disease. See these what were former beautiful pyrite cubes? They have these yellow specks on them. Those yellow specks are gold, because most pyrites have trace amounts of gold or silver in them as an impurity. And when the pyrite goes away, the gold or silver doesn't go away, and it coalesces like the silver did in the Proustite into these blebs. So you see how, and this would have a very nasty sulfury stink. And just imagine this happening in your mineral cabinet or drawer. It happens to mineral specimens, and it happens a lot in paleontological collections, as well as I was talking with Matthew about earlier. It's a really significant issue. So the immutability of minerals, not so much. What you have to do with Proustite is keep the light away from it and only show it selectively. What you have to do with pyrite, if you have beautiful pyrites in your collection, is use severe climate control and keep the humidity down and keep the oxygen level down. People even flood cabinets with nitrogen, with dry nitrogen, in order seal the cabinets in order to preserve the pyrite. And pyrite's also the same phenomenon is an issue for your house. You all know the issue in recent years, starting in 2005, of bad wallboard coming from China. Wallboard is made of gypsum, which is a sulfate mineral, but it often has little bits of sulfide in it as well as an impurity. And when that got pyrite disease, it caused that wallboard to emit significant amounts of sulfur vapor, caused lots and lots of problems. So I'll finish with a few pictures. We've gone a little bit longer than I wanted. I'll finish with some nice pictures of some of the minerals that you'll see in the exhibit that are ones that are particularly exciting to me, including rhodochrosite, tourmaline, azurite, prehnite, and minerals of the beryl family, including emerald, which is defined as green beryl. Aquamarine is defined as paler blue-green beryl. And beryl can also be pink and colorless, but it's a beryllium aluminum silicate, relatively common mineral. So let's look at some of these. We'll start with rhodochrosite. I love rhodochrosite. The prefix RHOD is a physical characteristic prefix in a mineral name that refers to a rose color, typically a pinky rose color. That's what RHOD means, and the word rhododendron for the plant refers to the pinky purple color that the flower is. So this is a classic sample from one of the best rhodochrosite localities, manganese carbonate localities in the world, which is in Alma, Colorado, in the Sweet Home mine. It's actually a silver mine, but it has spectacular secondary mineralization in it, producing these gorgeous pink, they're actually not cubes, they're actually rhombohedrons of carbonate. This is another Sweet Home mine sample. I don't think you have anything quite as nice as this, but nor do I. I have a very small one that approaches this, but nothing like this. These are really, really an attractive mineral. It's one of my wife's favorite minerals. This again, you can see, this is from Graham's Pocket in the Sweet Home mine. Often you'll see minerals labeled that specifically. They come from a particular place in a particular mine because it can vary a lot in the mine. I have a lot of minerals that were collected in the old Sterling Hill mine in New Jersey, which is a zinc mine. It's a treasure trove of zinc, famous zinc minerals. And if you go different places, or you can't now because it's all flooded, but when it was active, you could go there, and if you go different places, you could find, you know what different things you might find. And the minerals, as Matthew probably knows, the minerals from there are very famous because they fluoresce under ultraviolet light. So they're typically, those minerals from Sterling Hill and Franklin in northern New Jersey are centerpieces of fluorescent mineral displays. Another mineral that is a favorite of mine, this is just ordinary garden variety black tourmaline, exceptionally common in rocks, igneous rocks, metamorphic rocks. And in its black form, it looks like this, but you all know this other form. In fact, let's go back a second. You can see the sort of triangular, distorted triangular shape of the crystal with three edges coming up to this termination. And you can see the same symmetry, the same distorted triangular symmetry in these watermelon tourmalines. These are quite common, again, at the palapegmatite in San Diego County, California. And what they relate to is chemical zoning. Each of those colors relates to a slightly different chemistry of the tourmaline, and as it grew, typically in an open pocket in a pegmatite with fluid surrounding it, that's how these crystals could grow very big. The chemistry of the fluid was changing continuously, and so what was being deposited on the tourmaline changed continuously and changed the physical properties remarkably. This is a cut gem tourmaline from Newry, Maine. There's a famous tourmaline district in western Maine, Paris and Newry. And this color, this really beautiful color of blue, is almost unique to the Maine tourmalines. And again, I referred earlier to this. This is rubellite from San Diego County, California. This is the pink variety of tourmaline, and it makes the inside of the watermelon tourmaline. It's purely chemical effect. Azurite, which is a copper carbonate mineral. It's a complex copper carbonate hydrate. This is, and it's named, of course, for color, again, this azure blue. Its favorite companion mineral is malachite, which is actually the mineral involved in weathered copper roofs that have the green sheen on them. That's malachite. And you can see the malachite core here in a fibrous form surrounded by botryoidal azurite. This sample is almost certainly from the Congo. It's a very famous Central African district for copper. And this is another, I think this is one of the best azurite samples that I have ever seen. And radiating fibrous azurite. Not in my collection, I wish it were. And again, the two companion minerals, azurite and malachite, together as they often are. Prehnite. Prehnite's a very common mineral in Virginia. It's a fairly low temperature mineral, calcium aluminum hydrous silicate. And it can be colorless, it often is. It makes these beautiful bladed forms. It forms in openings in basaltic rocks in the Culpeper Basin, the Danville Basin, farther north in the Gettysburg and Hartford basins in the eastern U.S. So it can be colorless, but most often is a beautiful kind of mossy green color. And it often has magnetite with it. These are little specks of magnetite stuck to the surface of the prehnite. And prehnite with beautiful gem quality calcite. And finally, the beryl group minerals. This is a sample we recently acquired at Virginia Tech, donated by a very famous orthopedic surgeon, recently passed away from Suffolk, Virginia, Arthur Kirk, and he's donated many, many things over the years to us. This is a particularly nice one from Minas Gerais in Brazil. Dr. Kirk not only donated this sample of raw emeralds as they occur in the wild, in Brazil and Colombia and elsewhere, but also he donated this jewelry. And so you can see emerald in the raw and emerald in the processed form. Another example of beryl that is approaching being emerald. And this is a cut emerald. Notice that emeralds almost always have lots of stuff going on in them. The stuff going on in them is inclusions. Some are solid inclusions of other mineral phases, but most are actually fluid. Fluid inclusions that can be water primarily, or mixtures of water and carbon dioxide. They give very important clues to the conditions of formation of the mineral. But interestingly enough, there seems to be a connection, particularly in Colombia, of emerald with petroleum. And many emeralds actually have fluid inclusions that are hydrocarbon rich. So there was hydrocarbons flowing through the rock at the time, at high temperature, at the time that the emerald crystallized, and beryllium aluminum silicates. These were fluid inclusions trapped during crystallization. And then a much higher quality emerald. These are relatively rare and they have great value. A large emerald of this quality would be worth hundreds of thousands to maybe a few $1,000,000, particularly if you had matched stones. So that's it. I hope you enjoyed that. Gave you a bit of an insight as to what mineral collecting and mineral collections are all about, and a little bit of a preview of what you're going to see when you go over to the gallery. Thank you.
Well, as I mentioned before, we all have our reception beginning now at the Lora Office Gallery.